Okay, we have a continuity problem. So we're going to start off with using the definition of a continuity. Remember, there are three parts to our definition of continuity. Number one, the y value exists at that, right? We'll say is defined, because that's really what the math would say. The y value has to be defined at this particular value that we're questioning. Okay, in this case, it's x equals 2, right? For our example, we're using x equals 2 as being the point at which we are checking for continuity. Okay, checking for continuity at x equals 2. So number one, we have the y value is defined. Number two, the limit at that point exists. Okay, it actually has a number. Right, equals something, right? It's not, does not exist. And so the left side and the right side have to go to the same spot. And the third part of our definition, the y value needs to be equal to the limit. Right, so we could have a y value that's not in line with our limit, and then our function would not be continuous. So these are the three things we're checking for continuity, right? The continuousness. So here we have to prove that the function is discontinuous. So which one of these three things is going to fail? That's our question. Okay, so number one, let's check the y value at positive 2. Right, so this is what we're looking for. This is your C at x equals positive 2. So what is the y value at positive 2? Well, according to our piecewise function, when x equals 2, y is 1. Okay, when x equals 2, y is 1. So that means if I were to go 2 units to the right and 1 unit up, that would be my point for this graph. So f of 2 is positive 1. Bam, it exists, right? It's been defined. The y value is defined because we have x equals 2. Number 2, what is the limit as x approaches positive 2? Well, that we're going to use this equation. So everywhere that x is not 2, right, everywhere x is not 2, we're going to do this equation. And this equation it says here is negative 4x plus 7. Negative 4x plus 7. So it says if a is negative 4, right? So they're telling us that value of a. So how do we find the limit of our function? You plug 2 into our equation. So negative 4 times 2 plus 7 is negative 8 plus 7, which is negative 1. Okay, so when our equation, when x is negative 2, our graph is at negative 1. So that means that's our whole down here. So our graph would have a negative 4 slope and cross at positive 7. So this would be the graph of negative 4x plus 7. 1, 2, 3, 4, 5, 6, 7. That's the y-intercept, and it has a negative 4 slope. Okay, but notice the y value is positive 1, but the limit value is negative 1, right? So it says show that it is not continuous. So now we can come over here and we can write, let's write f of x, right? That's our graph, is, our analysis says not continuous at what x value? At x equals 2, right? All of these things are important parts. We need to say what function are we talking about? What is the conclusion of our math? And where are we talking about it? Because it could be fine at other places, just not at this particular place. Right? Because why? Right? This is our step number 3. We write because f of 2 does not equal the limit as x approaches 2. Right? That's the part of our 3-part definition that failed. The y value of positive 1 is not the same as the limit of negative 1. Okay? But you can't just say this part, right? You can't just say that's not continuous without showing the math. Okay, you have to do the math and say, oh, these aren't actually equal, so I can state this being that I've shown it mathematically over here. Okay, so don't jump to number 3 because you know it, right? Yeah, I'm sure that you do know it, but show the math to prove that you actually know it. Okay, let's look at our next example here for continuity. So we want to find a k value so that it will be continuous. Okay, so that the y value is the same as the limit. Okay, so mathematically speaking, we're going to set this equation equal to that equation, right? The y value from the red when x is 2 needs to be the same as the y value of the blue when x is 2. Okay, because that's our important part. That's the part that we're trying to make sure that they match up. The y values have to match up in order for our function to be continuous, right? Because that's about the limits. Where's the red graph going and where's the blue graph going? So we take our x plus 3 and we set it equal to kx plus 6. Okay, set your equations equal. That is our mathematical thing. The y value, these are both y values. F of x stands for y. So the y value of x plus 3, when x equals 2, so we're going to plug a 2 in for x. Okay, I guess we could have made a second step. Let's do that. Let's make a second step. 2 plus 3 equals k times 2 plus 6. Okay, so we set our equations equal. We replace x with the number in question. Right, we're trying to see what is happening when x equals 2. And now we just solve this for k. 2 plus 3 is 5 equals 2k plus 6. Right, minus 6 from both sides. And k equals that value. So our third one here is a little bit more mathematically intense. It wants to find an a and a b. So we have 2 variables, which means you think that this is somehow going to be a system of equations. Anytime we have 2 variables, you're going to have to make a system of equations to solve it. Okay, so get ready to do that. So there are 2 separate problems here. There's the issues of what's happening around -3, right? So just like the problem before, we're going to set our 2 equations equal when x is -3. And then there's the problem of what's happening at +1. Okay, so we're going to make 2 equations. We're going to set our top 2 equations equal. -17 has to equal ax plus b. And ax plus b needs to equal 3. Right? The y value of these 2 parts of our piecewise need to match up, and the y value of these 2 parts, the middle with the left and the middle with the right, have to match up. Okay, and the x value is going to be -3 for our top 2 equations. Right? That's the x value in question. And the bottom 2 equations is going to have an x value of 1. So we'll plug in a 1 right here. So -17 equals -3a plus b, and a plus b equals 3. Okay, so there's lots of ways that we can solve this system of equations. You could use substitution, as in we might solve this equation for b, okay, and take all of this and replace it over here, right? This is definitely one way that we could solve this, by using substitution, where we solve for one variable on one of our equations, right? Whichever one is easiest. Okay, you can solve for A or for B, does not matter. I chose B just because over here I don't have to multiply b by anything, right? I don't need to distribute. So I am just replacing b with 3 minus a. Okay, so that's why I chose to solve this one for b and replace it over there. You could have done elimination. That is a great method of solving systems of equations. Perfectly wonderful. So I'm going to combine my like terms. Negative 3 and negative 1 is negative 4a. Okay, I'm going to subtract my 3 to the other side, giving me negative 20. So with one division, I can figure out what my a value is. So now that we have our a value, we can plug it back in over here. B is 3 minus 5. B is negative 2. So if our values, right, from our equation were 5x minus 2, right, that was our equation, then 5x minus 2 would match up with 17 on the left, and 5x minus 2 would match up with positive 3 on the right, and our function would be continuous at every single value of x. Okay, so let's look at a couple of IVT problems also. So here's your three-part definition of the intermediate value theorem, right? We're continuous on the closed interval. Your end points are not equal, right? That's what f of a and f of b means. K is between these two y values. Okay, it doesn't matter which one is greater, which one is less than, but k is between them. And if that is true, then the IVT guarantees that there exists a number, right, on this closed interval where we have a y value that's the same. Okay, so there it says, in other words, it just tells you some stuff in words. So let's look at this problem. If the theorem holds, so we're going to check to see if the theorem holds, then it says find that x value. Okay, so there's a little bit extra here. Solve our problem. So we're given a rational function, right? This is rational, 1 over x minus 2. And our interval is from 2.5 to 7. 2.5 to 7. So our first question is, question mark, is our function continuous on that interval? Yes or no? Yes, it is. Is continuous on 2.5, so 2.5 to 7. Okay, where is our function discontinuous? At x equals positive 2, right? This function has a vertical asymptote at x equals 2. So as long as x is not 2, as long as 2 is not in your interval, then our function is going to be continuous, because functions are discontinuous at asymptotes, at removable discontinuities, and at jump discontinuities, which are irremovable, right? Because the limit does not exist. In order for a function to have a removable discontinuity, the limit must exist right there. Okay, number one, bam, it is continuous. It is not within our asymptotic range. Number two, let's find our endpoints. So what is f of 2.5? Okay, so if you want to write 2.5, that's fine. 2.5 makes more sense to me when I am doing math underneath the denominator. So 1 divided by 2.5 minus 2, okay, which is 1 over positive 0.5. 1 divided by 1/2 is 2. 1 divided by 1/2 is 2. There are two parts if I divide something in half. Okay, so there's one of my endpoints. One of my endpoints is 2, and let's check the other one, f of 7, which is 1 over 7 minus 2, which is just 1 over 5. So now we have to say, I'm going to come up here, is our value of 1/4, is 1/4 between positive 2 and positive 1/5? Right, 1/4 is 0.25, 1/5 is 0.2. So yes, right, this does in fact check out. Our k value is in between your two endpoints. Okay? So now we would say the IVT guarantees a c value, right? Therefore, the IVT guarantees. So because it is in fact continuous, the last thing says, all right, then find it. Go ahead and do the math. So when will 1 over x minus 2 actually equal 1/4? Right? What x value will that happen at? Okay? So it's pretty easy. Well, kind of. If you notice that let's don't do that. We're just going to cross multiply. Anytime we're trying to solve a fractional equality, right, which is known as a ratio, right, when these things are proportional, we cross multiply. So when will 4 equal x minus 2? Well, when x equals 6. So if x equals 6, we're going to have a y value of 1/4. And 6 is definitely between 2 1/2 and 7. Okay, so check all the parts of the IVT work. So one more example of our IVT. Okay, let's look at this one to see if it works. So number one, yes, our function is a polynomial. Polynomials are continuous everywhere, so it must be continuous on 0, 5. Okay, continuous on your closed interval. Number two, what are your endpoints? So we find what is f of 0. So that's 0 squared minus 0 minus 4. So f of 0 is -4. Okay, I trust that you know how to do the math with 0. You don't have to show me much of that work if you don't want to. So 5, f of 5 is 25 minus 15 minus 4, which is 6. So we have one endpoint of -4. We have one endpoint of 6. So yes, in fact, 1 is between -4 and 6. Okay? Therefore, the IVT guarantees that there's going to be a y value, or rather an x value, between 0 and 5, where y equals 1. So let's go ahead and do that math. 1 equals x squared minus 3x minus 4. Okay, we want to know what is our x value when our y value is 1. So we're going to make this into a quadratic by subtracting 1 from both sides. 0 equals x squared minus 3x minus 5. Are there numbers that multiply to give us -5 and add to give -3? Right? That is not a thing. So this polynomial, this quadratic, is not factorable. This is not a factorable quadratic, which means we have to use our fantastically fun quadratic formula. So the negative of b, our b value is -3, plus and minus. No, we only want the plus side because we want between 0 and 5. If you do the minus side, then you're probably going to get a negative number, and that's not in your answer interval. Plus the square root of -b squared. -3 squared minus 4 times a, which is 1, times c, which is -5, all divided by 2 times a, which is 1. Remember, all these values are coming from a is your x squared component, b is your x component, and c is your constant, right? A, b, and c. So the negative of -3 is +3, plus the square root of 9 plus 20, all divided by 2. Okay, -4 times -5 is a plus. This comes out to 3 plus the square root of 29 divided by 2. Okay, now I'm assuming because the intermediate value theorem says so, this number is less than 5. That number is less than 5. And just to take a gander, root 29 is bigger than 5, right? Because root 25 is equal to 5. So maybe this is 5.2, 5.3. If we add that to 3, that's 8.3, right? So maybe the top is about 8.3. 8.3 divided by 2 is 4.15 or 4 point whatever. 4.15 is in fact less than 5 and bigger than 0. So I am okay with this answer. It matches all of my requirements for my solution. So if your quadratic is not factorable, then you have to solve it algebra 2-wise by using the quadratic formula. Okay, so there's some more work on intermediate value theorem and continuity.